do some complicated. This is the question. So light of wavelength see, if you can't solve this direct question, it will be very tough for you to do the next numericals of the series. This is the easiest one. Light of wavelength 5000 angstrom falls on a double slit having small d equal to 2 mm. Small d means the separation between the two slits S1 and S2, and capital D equal to 2 meter. Calculate first part. Separation of.
Sir, we had already done.
We have done this numerical.
Yes, sir, in the last class.
Okay, so fine. We have already done this formula based numerical. So whatever we'll do now will depend on this question. So basically, the topics or the formula that we'll be using today are for the bright fringe. What is the formula for the separation of nth bright fringe from central maxima? Akshay? Akshay, formula for nth bright separation of nth bright fringe from central maxima. What is the relation? Bhishma?
X d by d.
And lambda d by d, right? N is the number of fringe. So what is the value of n for the first bright fringe? Akshay? What?
1.
Yeah, n equal to 1. And what n equal to 0 stands for which fringe?
Central.
Yeah, n equal to 0 stands for central bright fringe. Similarly, we have derived a relation for the dark fringe also. Krishna, do you remember that relation? We derived in the last class.
Ma'am, yes, sir. 2n minus
Yes.
minus 1 by 2.
2n minus 1 lambda d by 2d.
Yes, sir.
Similarly, we derived an expression for the fringe width also. Minashi, what's the relation for the fringe width? Sorry?
Beta equal to lambda d by d.
Lambda capital D by square. We derived one more expression for the angular fringe width. Only what was that?
N is equal to lambda d by 2d.
Nah.
So lambda by small d.
Lambda by small d. Then we calculated the expression for the fringe width in medium. Fringe width in medium is fringe width in air divided by the refractive index. So these are the relations that we'll be using in the next question. Yes, note down this question. And while writing this question, just try to identify what is small d, what is capital D, what is the wavelength of light. Please write it fast. Huh? We have to finish this chapter today. Yes, have you written the question? Noah, Nabil. Did you write the question? Yashika, Noah, did you write the question?
Sir, writing.
जल्दी लिखो, बहुत स्लो लिखते हो।
सर इसके बाद हम रे ऑप्टिक्स स्टार्ट करेंगे।
Yes. इसके बाद we'll do diffraction and start with ray optics.
Sir, what we have to calculate? क्या लिखा है? मैं calculate.
Okay, you have to calculate the separation where the two bright fringes will coincide. Okay. I believe everyone have written the question at least. So see, in this question, what is capital D? This 1.4 meter is the capital D. How much is small d? 0.28 mm is the value of small d. There are two wavelengths, 100 nanometer, that's lambda 1. 600 nanometer, that is lambda 2. You have to calculate least distance from central bright maximum bright fringe of the two wavelengths will coincide. So instead of one wavelength, you have two wavelengths now. So you will have two interference patterns. Instead of a single wavelength, now you have two wavelengths. So you will have two interference patterns. Okay, so this is the system. This is your double slit pattern, slit S1 and slit S2. And this is the screen. This is point P on the screen. So from slit 1 and slit 2, two light waves are coming. So basically two wavelengths are coming. Let's assume one is blue, which I am calling as lambda 1. And another is red one, which I am calling as lambda 2. Two wavelengths are coming. So you will be having two interference pattern on the screen. So you have two interference patterns. One is for the blue wavelength, another is for the red wavelength. At the center of the screen, this point, the bright and dark fringes, the bright fringes of the blue and the red will coincide. So at the center, the bright fringe of blue color and the bright fringe of red color will coincide. This is the central maximum. This is the central maximum. So at center, the bright fringes, both the wavelength is coinciding. Next, you have to decide which fringe of lambda 1 and lambda 2 will coincide. Like, it's possible that first bright or second bright fringe of blue wavelength and third bright fringe of red color can coincide. Or you can say that third of blue color and the fourth of red color will coincide. You have to decide which bright fringes will coincide. The first set of fringes which are coinciding are central bright fringe, or you can call it as.
Show me the question.
Sorry?
Can you show me the question?
Yes. You can take screenshot of the question. So the first set of bright fringes that coincide is central maxima. You have to decide after central maxima which set of bright fringe will coincide. Second and third can coincide, third and fourth can coincide, fifth and seventh can coincide. You have to decide which will coincide. So for this, what we can do is, let's assume that nth bright fringe nth bright fringe of lambda 1 wavelength will coincide with mth of lambda 2. So nth bright fringe of lambda 1 will coincide with mth fringe of lambda 2. So if these two fringes are coinciding, that means this separation of the nth fringe of lambda 1 and this separation of mth fringe of lambda 2 should be. See, those two fringes can only coincide if their separation is same. So you can start with this term, yn is equal to y. That's a simple thing. Instead of a single wavelength, you have two wavelengths. So you will have two interference patterns. You have to decide which set of fringes will coincide. Bright fringes will coincide. So fringes will coincide only if the separation is same. So you can say that separation of nth fringe from central maxima is equal to the separation of mth fringe from central maxima. So you can say yn will be equal to y. Or you can say n lambda 1 capital D by small d is equal to m lambda 2 capital D by small d. Small d will cancel small d. Capital D will cancel capital D. And you can write that n by m will be equal to lambda 2 by lambda. What is lambda 2? Lambda 2 is 800 nm is lambda 1. Lambda 2 is 600 nanometer. So this is 600 divided by 800 gets cancelled out. So this is 3 by 4. N by m is 3 by 4. Or you can say that n is 3 by 4m. So you have to decide the value of n and m for which the fringes will coincide. So if I put m equal to 1, means first bright fringe of second wavelength. Then you get n equal to 3 by 4. See, the number of fringe cannot be in fractions. The number of fringe should be a whole number. It should be an integer. So that's not possible. Means first bright fringe of second wavelength cannot coincide with any bright fringe of first wavelength. So if you put n equal to 2, then again you will get fraction. So can you guess what should be the minimum value of m for which n is not a fraction, n is an integer?
4.
4.
Put m equal to 4. We get n equal to 3 by 4 into 4 gets cancelled out. So n equal to 3. So you can say that third bright fringe of lambda 1 will coincide with fourth of lambda. Now, once you have the value of n, it's very easy to calculate yn. Yn is n lambda capital D divided by small d. Lambda 1, we can substitute the values. N is equal to 3. How much is lambda 1? Lambda 1 is this. It's 800 nanometer. Nanometer means it's 10 raised to the power minus 9. Capital D is 1.4. Divided by small d is 0.28 mm into 10 raised to the power minus. So this is the value of yn will calculate. Omar, m is equal to 4, we get the value of m equal to 4 because this is the relation between n and m. N is 3 by 4m. The value of n should be an integer. So the minimum value of m for which n comes out to be an integer is 4. If I put m equal to 1, then your n will be 3 by 4. If I put m equal to 2, your n will be 3 by 2. So the first value of m for which n is an integer is 4. Clear?
Yes, sir, clear.
So this is what you are supposed to calculate. So note down the solution. We'll do one more.
Sir, can you show me the question once again?
Yes, please take the screenshot. Jasola, have you taken the screenshot?
Yes, sir. Done.
Is it clear? Uneeb,
Yes,
Miraj?
sir.
Second scroll.
Yes.
Any scroll.
Yes.
सर वेव ऑप्टिक्स में कुछ डिलीटेड
Sub deleted instead of interference and diffraction, polarization, Doppler's effects. Even 50% of diffraction is also new.
Thanks.
So this is the last major topic of wave optics interference. उमर जल्दी लिखो. Also from next week onwards, I'm starting a revision test series. We'll get the scheduler. So in every class, we'll be having a test of 30 minutes. So it would be your choice. You can give that test at 8 o'clock, 8 to 8:30, or you can give that test after the class. Half an hour test, right, starting from chapter number 1. In every class, we'll have a 30-minute test. So the first test will be on Monday. The topic will be chapter number 1. Before Gauss law. It's up to electric dipole. Everything before Gauss law will be the syllabus of first test. Aji, can I scroll it? Everyone are written, huh? Let's do the next question. Again, a very good question. Write down this question also. Yes, Nabil, but you don't need that crash course, right? The chapter 1 and 2 that you have missed will do it, the revision. It's already going on, but I don't think that you need that cache host. You joined from chapter number 2, no, Nabil? Three. So for 1 and 2, I'll give you back. Don't worry. Just let me finish this syllabus. Then I'll repeat chapter 1 and 2. Haji, everyone had written the question? No, I will finish it by the end of third week of December.
Sir,
But
OP
by
क्या
the
है
second
इसमें?
week of December, we'll finish everything as then the modern physics. So modern physics takes 3-4 lectures.
सर यहाँ पे OP क्या है?
OP is part of question, I'm showing you. This is OP. Okay, let's start with this numerical also. So intensity of central maxima in Young stable state experiment is I naught. I naught is the intensity of central maxima. The intensity of light coming from the source S1 is some I1. Intensity of light coming from the source S2 is some I2. I1 and I2 is not given. The intensity of the central maxima is given. So what we can do in the first part is we can use the formula for maximum intensity and get the value of I1 and I2. So what we can do here is we apply this relation that I max is, first of all, we require the intensity of the individual fringes, I1 and I2. We first calculate I1 and I2 and then we will proceed. Okay, the maximum intensity, the relation for maximum intensity in Young's double slit experiment is this. I max is root I1 plus root I2 whole square. If I1 is equal to I2, what you can do is instead of I2, you can put I1. And your I max becomes, it's root over I1 plus root over I1 whole square. You can write I max as it's twice of the root over I1 whole square. The maximum intensity, the intensity of the maxima is given, which is I naught. So instead of I max, you can write I naught. I naught is 4 times I1. So you can say that I1 is I naught divided by 4. So this is I1. So we know the intensity of individual slits. So I1 is equal to I2 is equal to I naught. In the next part of the question, it's given if distance OP equal to 1/3 of fringe width. OP means the separation Y. Now the next thing is if the distance OP equal to 1/3 of the fringe width. This distance OP is nothing but yn. X, it's given as x, but in our derivation we took that distance as yn, which is given as 1/3 of fringe width beta by 3. Fringe width is lambda capital D by small d into 3. This is x or y. So over this point, you have to calculate the intensity of the light. To get the value of intensity of light, you should at least have the value of the part difference and the phase difference. So using this relation that yn is lambda d by 3d, you can calculate the value of part difference. See, in the previous derivation, the derivation that we did in the last class, we have derived this one expression. Where is it? Yeah, we derived this expression. We have derived the relation between the part difference, yn, small d and capital D. X is yn, small d and capital D. Using this relation, we can get the value of the part difference. So using that value of yn, which is 1/3 of the fringe width, we can calculate the value of the part difference. Once you have part difference, you can get phase difference. Once you have phase difference, you can get the value of the resultant intensity. Part difference is yn to small d divided by cap. This is the value of yn that we know is lambda capital D by 3d. Let's call this as equation number 1. Let's call this as equation number 2. Let's call this as equation number 3. So what we can do is we can substitute 1 and 3. So when we substitute 1 and 3, we get delta xn is yn, which is lambda d by 3d into small d by cap. So we get that the part difference is lambda by 3. So once you have part difference, we need phase difference. Yashika, what's the relation between phase difference and part difference? उमर, कभी कभी ना तुम्हारे क्वेश्चन देख के लगता है तुम कभी पीछे का पलट कर नहीं देखते हो. मैक्सिमा इज द थिंग दैट वी डिराइव्ड इन द. और उमर, मेरी क्लास जब तक खत्म ना हो जाए ना अप टू 10:30, आप में से कोई लॉग आउट नहीं करेगा, अदरवाइज मैं डाउट्स लेना बंद कर दूंगा. स्पेशली अर्पित, उमर और कौन है ये, मेराज. अगर क्लास 10:30 तक है, आई वांट यू ऑल टू बी इन द क्लास अप टू 10:30. ना आप लोगों ने मजाक बना रखा है. क्लास में जैसे ही 9:55 हुए आप लोग लॉग आउट करना शुरू कर देते. क्लास 10 से 10:30 तक एक्सटेंड हो सकती है. जब तक मैं अनाउंस नहीं कर रहा कि क्लासेस ओवर, आप में से कोई नहीं छोड़ेगा. आप क्लास मिस करते हैं लास्ट की क्लास, और मेरे लिए प्रॉब्लम हो जाती है आपको समझाना. मतलब वो जो चीजें मैं लास्ट 10 मिनट 15 मिनट्स में समझा रहा हूँ वो तो स्किप हो जाती है. एंड ऑल्सो अर्पित, उमर, द टाइमिंग ऑफ द क्लास इज 8:30. I wait for at least 5-6 minutes, then I start the class, but I want you to be in the class by 8:30.
Sir, I have my another class, so I get late.
अर्पित, ये रोज का है, किसी तरह से सेट करो इसे.
Sir,
मतलब ये
because
हमारा
वो
पूरा
Monday
टॉपिक छूट
alternate
जाता
होती है.
है. ये हर क्लास में होता है कि स्टार्टिंग का लेक्चर तुम्हारा मिस हो जाता है. और उमर, आपके साथ भी ये, आप भी लेट ज्वाइन करते हैं, बीच में आप लॉग आउट कर देते हैं, फिर आप बिल्कुल आइडियल हो जाते हैं कि मैं पूछ भी रहा हूँ तो आपको उससे कोई मतलब नहीं. ऐसे फिजिक्स क्लास नहीं हुआ फिर. एंड नबील, आप भी, आप कहाँ थे लास्ट क्लास में? नबील खान, यू वर इन द लास्ट क्लास.
Yes, sir. I was.
कैसे ऐसे कैसे हो सकता है? रेगुलर क्लास का टाइम है वो तो. आप उस टाइम पे कोई और क्लास कैसे रख सकते हैं? दिस 8:30 इज द रेगुलर टाइम ना, कोई चेंज तो नहीं हुआ. ऑलरेडी ये क्लास आपकी शेड्यूल है, तो उस टाइम पर आप कोई और क्लास कैसे रख सकते हैं? एंड नबील, दिस इज फिजिक्स. लाइक एक लेक्चर छोड़ने के बाद ना पता नहीं कितने लेक्चर्स तक कुछ नहीं समझ में आए. थिंग्स आर इंटरलिंक्ड. सुनो मैं. In interference, light from the two slits, light waves from the two slits come and they superimpose. When they superimpose, they make bright fringe, which is sometimes known as maxima. And they can also make dark fringes, which is sometimes known as minima. The intensity of maxima or the bright fringe is I naught, which is given. Now, part difference we have calculated, which is lambda by 3. What's the relation between part difference and phase difference, Yashika?
Sir, phase difference is equal to 2 pi by lambda times part difference.
2 pi by lambda multiplied by the part difference. 2 pi by lambda into part difference, which is lambda by 3. It gets cancelled out. So you have 2 pi by 3. So once you have phase difference, I need the resultant intensity. Noah, what's the formula for resultant intensity?
So under root I1 square, I1 plus under root I2.
That formula was for the maximum one. I'm not asking about the maximum. It was I1 plus I2 plus 2 root over I1 root over I2 cos phi. The value of phi is 2 pi by 3. So you can write resultant intensity as I1, which is I naught by 4 plus I2, which is I naught by 4 plus 2 root I1, I naught by 4 root I2, I naught by 4. And this is cos phi. Phi is 2 pi by 3. How much is cos 2 pi by 3, Uneeb? I naught by 4 plus I naught by 4 is I naught by 2. Root I naught by 4, root I naught by
1 by 2.
1 by 2. 2 pi by 3 is 1 by 2 or minus 1 by 2?
Sir, yes, sir. -1.
It gets cancelled out. So the resultant intensity is it's I naught by 2 minus I naught by 4, and that comes out to be I naught. This is the formula for this. Fine. So this is what you're supposed to do. See, all these last 3 questions are from the sample papers of CBSE. Note it down. Is it clear, Nabil?
Yes.
Ahmed? Omar, is it clear now?
Sir, can you scroll up for a second? Yes, sir.
Okay, now let's do the next question. Can I scroll it now if you have written? Akshay, Krishna, Krishma.
Yes.
So one
Yes.
minute. Done, sir.
Okay, this will be a homework, just note it down. This is a modified Young's double slit experiment. This, in original experiment, we place this source at the perpendicular bisector. Now this source is not at the perpendicular bisector. Note down the question. This will be a homework.
Sir, all the 3 bits are homework.
Yes, this is a homework. If you want hint, you can take screenshot. You can take screenshot of the solution if you want. So if something very, very tough comes from the interference, Young's double slit experiment, then that is this question. Please take a screenshot of the solution. This will help you. Just take screenshots, huh?
Sir, can you show the second one?
So can you show the second one? So on second one.
Just take the screenshots only. No need to write the whole solution. Just take screenshot. This is the second one. This slide you are asking or the previous one?
No, done, sir.
Okay, the next is the intensity distribution curve. To draw intensity distribution curve, we consider both sources to be identical. If both the sources are identical, that means I1 is equal to I2. If you want to calculate a minimum intensity, the formula of minima was root I1 minus root I2 whole square. This is what we have derived in the first lecture of interference. It comes out to be 0. If we calculate I max, it's root I1 plus root I2 whole square. That comes out to be 4I1. See, root I1 plus root I2. I2 and I1 are equal. It will be 2I1 and square is 4I1. So if our sources are identical, then in minima, the intensity comes out to be 0. For maxima, the intensity comes out to be 4I1. So that means energy transfers from dark to bright fringe. So this is what happens in interference. The intensity of light get transferred from the dark fringe to the bright one. And if you draw an intensity distribution curve, just one more thing. But if your sources are incoherent, then interference is not possible. Then the intensity that you will be getting is I1 plus I2 only. And this I1 plus I2 is independent of phase difference. The intensity that you get in incoherent sources is independent of phase difference. Also, what are the phase difference for the minima? Vishma, what are the values of the phase difference for the minima? Phase difference was pi, 3 pi, 5 pi. For all these phase difference, we get a minima. And the value of phase difference for maxima, it was 2 pi, 4 pi, 6 pi. These are the values of the phase difference for the maxima. So if you want to plot something like intensity versus the phase difference graph, or the intensity versus the part difference graph. If your part difference is 0, then you get a maxima intensity is 4i. If your part difference is lambda, then you get again a maxima, your intensity is again 4i. If your part difference is minus lambda again, then you again get a maxima, your intensity is 4i. But if your part difference is lambda by 2, 3 lambda by 2, lambda by 2, 3 lambda by 2, then you get a dark fringe, and the intensity of dark fringe is 0. So if I connect all these dots, I get this type of curve. But if your sources are non-coherent means there is no interference. The intensity will not depend upon the phase difference. So you'll get a straight line. No matter what the phase difference is, the intensity will always remain 2i. This is for incoherent addition. But if your sources are coherent, then you get strictly maxima and minima. Note down this intensity distribution curve. So these are identical sources which are coherent. This is possible only for coherent sources, not for non-coherent sources.
Sir,
Hmm.
so can you explain the graph again, sir? The intensity graph.
Do you remember the value of phase difference and part difference for the bright and the dark fringes? No.
No.
See, in the first lecture of interference, we have derived that if you want a bright fringe, then your part difference should be n lambda. And the value of n will start from 0, 1, 2, 3, and all. So if you put n equal to 0, then your part difference is 0. If you put n equal to 1, then part difference is lambda, 2 lambda, and so on. So for lambda 0 and 2 lambda value of part difference, you get a bright fringe. For a dark fringe, we have derived that the value of part difference is 2n minus 1 lambda by 2.
Yes, sir.
So if you keep on changing the value of n, the part difference will keep on changing. It will be lambda by 2, 3 lambda by 2. These are the part difference for which you get a dark fringe. From these calculations, you can see that the intensity of the dark fringe or the minima is 0. Intensity of the bright fringe or the maxima is 4i.
Yes, sir.
So what I do, on the x-axis, I take part difference. If part difference is 0, which fringe you will get, bright or dark?
Bright fringe.
Bright fringe. When your part difference is lambda by 2, which fringe you will get?
Dark.
When the part difference is lambda.
Bright fringe.
3 lambda by 2.
Dark fringe.
And for the dark intensity is 0 and for bright intensity is 4i, right?
Okay.
Similarly, you can do to the left hand side also. Huh?
Yes, sir. Got it.
Then I connected all dots. Is it clear?
Yes, sir. It's clear.
But when your sources are non-coherent, there is no interference. Means it's just addition of light, nothing else. It's I1 plus I2, it's always 2i. It does not depend upon the phase difference. Phase difference will play its role only if there is interference. Only if your sources are coherent. If your sources are not coherent, then phase difference will not play its role.
So for non-coherent, we get lesser values.
Sorry.
For non-coherent, we'll get usually lesser values.
On non-coherent, you will always get 2i. It's normal addition of light, like I1 plus I plus I will be 2i. There is no interference.
Okay, sir.
So there won't be any bright or dark fringe. You will get a constant intensity. It's just like what happens in your room when you switch on 2 bulbs. Like you bring one bulb from the market, its intensity is high. Then you take another bulb, its intensity is high. When you switch on both the bulbs together, the resultant intensity is too high. You don't get bright or dark fringes because the bulbs that you have are non-coherent. So throughout your room, you will get a uniform intensity 2i, irrespective of the part difference. But instead of 2 non-coherent bulbs, if you can manage somehow 2 coherent bulbs, then in your room, you will get a pattern. At some point, you will get a dark spot. At some point, you will get a very, very bright spot. I mean, intensity for that. That is your interference. In interference, energy transferred from the dark fringe to the bright one. Tell me once you have written.
Yes, sir.
Okay. After this curve, there is one more theoretical question. The question is on sustained interference. See, what is sustained interference? Sustained interference means permanent. It's a theoretical question. Permanent interference means interference pattern in which you can identify bright and dark fringes. The intensities does not change with time. You have a good contrast between bright and dark fringes. This type of interference is known as sustained interference. So position of maximum minimum intensity does not change with time. And these are the conditions to obtain a sustained interference. The first one is sources should emit continuously light of same wavelength or frequency. You can say that sources should be coherent. So this and this together makes coherent sources. So for a very good contrast, both the sources should be identical. The third point says, means I1 should be equal to I2. If I1 is equal to I2, then you can say that the intensity of the dark fringe will be 0, but that of bright fringe will be 4 times. So there is a very, very good contrast between bright and dark fringe. The 2 sources should be narrow. You should have a very narrow source. Otherwise, what will happen if you have these sources means these slits are, you should have a very narrow slit. If you take very broad splits, then bright and dark fringes can overlap and you will not get a sustained interference. Sources should be monochromatic. Monochromatic means sources should emit light of single wavelength. Otherwise, the bright and dark will just overlap it. The next condition is small d. The separation between the two slits should be very small. And the separation between source and the screen should be very large. Capital T should be large and small d should be very, very small. There is one more condition, although it's written in NCERT in one line, but NCERT have not discussed this condition in very detail, but you should at least know this condition. This is the source slit. These are the double slits. Separation between source slit and double slit is capital S. Separation between S1 and S2 is D. So small s by capital S should be less than or equal to lambda by D. Small s is the size of the source slit, capital is the separation between them. Lambda is the wavelength of light, the separation between S1 and S2 is D. No matter what happens, this condition should always be satisfied. Small s by capital S should be less than or equal to lambda. If you disturb this condition, then fringes will start overlapping each other and you will not get a sustained interference. Do it, right? No, or instead of writing, if you want, you can take screenshot. So what you would prefer? You will take a screenshot or you will write everything?
The screenshot. We'll
Take
write it
screenshot.
later.
Beautiful. But please write down this in notes. Huh?
Yes, sir.
Second scroll up.
Scroll up, yes. This one?
Yes, sir. Sir, little down. Yes, yes. Good.
Taken? Just take screenshot. Huh? You can write it after the class. Also. Just don't waste time. But it's a very, very famous conceptual question. What are sustained interference? What are conditions for a sustained interference? You should know these conditions.
Second, show the third, fourth one. So third and fourth. Done.
Sir, what does size of source slit mean?
Size of source slit means the dimensions of the source slit. If you are taking your source slit to be a sphere, then we are talking about the diameter of the sphere.
Okay, sir.
If you're taking your source slit to be a rod, then we are talking about the length of the rod. If you're taking it to be a tube, we're talking about the length of the tube. Okay, so that was about interference. And after this, you have to do this example of NCERT 10.4. All these points that we have discussed for sustained interference, all these F questions are based on those things only. Write down this thing. Example 10.4 of NCERT. You have to do it. If you look at the previous year's questions, you will find many questions from this example only. Example number 10.4. Okay, this finish our interference. Let's start with the next. Example 10.4. See, diffraction is not in very detail. Interference was in very, very detail, but not diffraction. Now let's see what does diffraction means. Diffraction simply means the bending of light. The phenomena of bending of light is known as diffraction. So, okay, if you want to explain diffraction, let's take this example. This is an obstacle. This one here is an obstacle. This is one obstacle. You can consider it as a wall. You can consider something which is opaque. Light cannot pass through it. And you incident light waves over it. Light waves, right, are coming. Yes, you can take it to be a cardboard. Then this is the screen here. This is the screen here. We expect that since this object is opaque, so just behind this object, we should get its shadow. We should not get light in this region. Since light rays cannot pass an opaque object, so we expect here, from here to here, there should not be any light ray. But what happens instead is, when the light rays passes through this obstacle, they gets bent. They gets bent. And this bending is known as diffraction. This bending of light is diffraction. And then what happens next is, when the light rays bend, they superimpose with each other. And due to superposition, they will give rise to a similar pattern of bright and dark fringes. Although there are few differences between the pattern of this diffraction and that of interference that we will discuss later, but this is what we call diffraction, the bending of light. But for bending, there is one condition. The corners, like these corners from which light bends, the size of these corners should be less than or at most equal to the wavelength of light. If the size of corners is greater than the wavelength of light, then it will not bend the light waves. It will simply scatter the light waves. It will simply reflect the light. Light waves can bend only if the size is comparable to the wavelength of light. So this is what we call diffraction. Phenomena of bending of light around the corners of a small obstacle or aperture and its consequent spreading in the region of the vertical shadow is called diffraction. So for diffraction, size of aperture should be very, very less than the wavelength of light. Next type of diffraction. We have two types of diffraction. One is Fresnel diffraction and another is Fraunhofer. To understand Fresnel diffraction, take this example. See, this is a slit, single slit. This is an opening. This and this is an opening. The single slit. And this is the light source. When light source passes through this opening, they gets bent. This bending is diffraction. But light source will bend only if the size A of the slit is either less than or it's equal to the wavelength. Then only light will bend. Next, what we can do is we can divide diffraction into two types. Diffraction can be Fresnel or it could be Fraunhofer. In Fresnel diffraction, the separation between source means the light source, slit, and there should be one screen. The separations are finite, then we call it as Fresnel. In Fraunhofer, all the separations are infinite. The separation between the source, separation between the slit, and the separation between the screen is infinite. That's the Fraunhofer diffraction. You have to do Fraunhofer diffraction. Fresnel diffraction is not a part of it. Note it down. We'll start with Fraunhofer diffraction.
Sir, the light bends because of that opaque object.
The light bends from the corners of the opaque object. It bends from the corners. Written? Umar, that we will discuss. This is the next topic that you are asking. This is the next thing that we will discuss.
Done, sir.
Okay. And always remember that for diffraction, the size of the aperture, the size of the obstacle from which light is getting diffracted should be less than or at most equal to the wavelength of light. Otherwise, you won't find any diffraction.
Sir, can you scroll up?
Sorry.
Sir, can you scroll up first?
I should scroll it down.
Sir, scroll up first.
Up. Your voice is cracking. You're asking me to scroll up?
Yes, sir.
Yes. Over in the second diagram, the light waves are coming and they're getting bended. So you can say that parallel rays are coming. Plane wavefront means parallel rays are coming and they are getting diffracted. The rays are getting bent. So if you want to see this, I have drawn a plane wavefront and the diffracted wavefront. If you don't know wavefront and you want to see this thing in the picture of rays, then these are the incident rays when they pass, they gets bent in this way. These are rays. But we started wave optics with a wavefront. So these are the wavefront, the incident wavefront and the diffracted wave.
Sir,
Sir,
what's
we
the
write
example of
as well.
pencil?
Yeah, the wavefront bends and becomes spherical wavefront. Yes.
So
Yes,
should we
but
write the first one as well?
no, Omar, when they say the parallel rays are coming and when they bend, the pattern of the rays change. Similarly, the rays simply reflect wavefronts. You can relate rays and wavefronts. The rays are perpendicular to the wavefront. So as you can see here, when the rays passes through this single slit, they gets bent. The same bending when you explain in terms of wavefront and you say that plane wavefront, when passes through the slit, they gets bent. Bend means they become spherical. Yes, the plane wavefront is getting converted into the spherical. Aji, can I scroll it?
Sir, wait, sir.
Miraj, you have my contact number? Raj Rahman. Raj.
Yes, sir.
Rahman, just I have to discuss something with you. Just WhatsApp me. I don't have your contact now. I'll call you after the class.
Sir, me?
Yes, Miraj. You have my contact number?
Yes, sir, I have.
Okay, just leave me a WhatsApp. I'll call you after the class. I'll discuss something. Okay. Single slit diffraction. See, the single slit diffraction experiment is this snapshot is that of an actual experiment. Okay, so this is a single slit. See, this is single slit. The opening from which light can pass, and you can say this red spot. This red spot means behind this single slit there is one laser source, light source. So you incident a light source over the single slit. When light passes through the single slit, then it bends, superimpose, and you will get these type of pattern of bright and dark fringes. This spot here is known as the central maxima. This spot here is known as central maxima. After this central maxima, you can see if I just, you can see this line, this one here. So this is the dark spot. Then you have a bright spot. Then you have a comparative dark spot. So in diffraction, dark spot doesn't mean it's completely black. Dark spot simply means the intensity is slight less than that of maximum. So we call this as maxima, then you have minima, then you have another maxima, then you have minima, another maxima, then you have minima, maxima, then minima. This is the diffraction pattern that we have to calculate. In fact, we don't have to derive everything, we just have to write the results. Diffraction is not in very much detail in your syllabus. So this is the diffraction pattern, single slit experiment. So you have a single slit, you incident a laser light over the single slit. When the light passes through the slit, it gets diffracted. Diffracted means different parts of the light gets superimposed each other, and due to superposition, you get this bright and dark spots. So this bright spot here is the central bright spot. And then you have dark, bright, dark, and all. So if you compare this with interference, there are few differences. The first is, in interference, all bright and dark fringes have same width, but you can see the central one is white. After central one, you can see the width is decreasing. So in diffraction, the width decreases. Even the intensity is decreasing. But if you take interference, the intensity of all fringes is same. So that is actual single slit diffraction. And this is how we draw it. It's a Fraunhofer diffraction. What does Fraunhofer diffraction means? What does Fraunhofer diffraction means, Minashi? We just have discussed Fraunhofer diffraction. What does Fraunhofer diffraction mean? Arpit, what does Fraunhofer diffraction mean? No one remember. Yashika, what is Fraunhofer diffraction? Okay. Akshay, Nabil, is there anyone who know what is Fraunhofer
Sir,
diffraction?
separation between source and slit
Suppression
is
will be
infinite.
infinite.
Yeah.
In Fraunhofer diffraction, the separation between source and slit
And slit is infinite.
infinite. If the separations are infinite, then we call it as Fraunhofer diffraction. So see here, in this experiment, this is the slit. This is the slit, single slit. This is the source of light. You want source to be infinity. Source to be at infinity means you want parallel rays. So there are two ways to get parallel rays. The one is you can put your source at infinity and the parallel rays will come. The another thing is you can use a convex lens. You place your source at the focus of the convex lens. Rays will come. After refracting from the lens, they becomes parallel. So the motive of Fraunhofer diffraction is you need parallel rays. So parallel rays can be obtained in two ways. One way is you can put your source at infinity, or you can use a convex lens. So here we are using a convex lens. We use a convex lens here, put the source at the focus, the rays comes and it becomes parallel. When these rays passes through the slit, see, they are bending. You can see the bending of light. Some rays are not bending, they are going straight. Others are bending at some angle theta. So this bending of light is known as diffraction. So the light waves will bend at several angles. Few may go in this direction, some can go in this direction. So light waves can bend ideally in any direction. But all these rays are parallel. They will converge at infinity. But if you want to see the bright and the dark fringes, what you can do is you put a convex lens here. When these rays passes through this convex lens, they get converged at the screen. So this is the screen. So these parallel rays gets converged at the center of the screen. This is known as central bright fringe. these rays which bend at some angle theta, when they converge, they can form a bright fringe or a dark fringe. So they will make some nth fringe. The separation between the central bright fringe and this nth fringe is yn. We call this as linear fringe separation. This is convex lens. This is the single slit. No, this is the simple experiment. This is diffraction. Light comes from the single slit and they get bent. So these rays are not bending. These rays are bending at an angle theta. The size of the slit from A to B is represented by A. The separation between the single slit and the screen is capital D. Capital D is separation between single slit. And this theta here represent the angular fringe separation. So say if fringe is here, then the value of theta will be greater. If your fringe is here, the value of theta will be much greater. So this theta represents the angular fringe separation. This Yn is similar to that of Young's double slit experiment. In double slit experiment, this represents the linear separation. Here, this theta represents the angular separation. Please draw this diagram. See, we won't draw this thing, but at least draw this diagram. This is diffraction
So
of... Yes.
So the rays won't deflect downwards?
Yeah, they can diffract downwards also. They will diffract here also. But for the sake of calculation, we need one set of rays. So I'm taking this one only. Otherwise, rays will bend in all directions. Here also, here also, here also. But for the sake of calculation, we are drawing one. Please draw this diagram. Nabil Ahmed, you got your marks of physics?
No, sir. Our exam just last week it was over.
See, I went through the papers of most of you. The question paper that you are getting is substandard. The board's exam, your board's exam is foreign, CBSE foreign, right? CBSE foreign is tougher than CBSE All India or CBSE Delhi. If you go through the previous year's questions, CBSE foreign have some questions which are tough than the questions that are usually asked in CBSE All India. But the type of paper that I went through of your school exams, they ask some straightforward questions. So the paper that you will get in boards will not be so straightforward. You will have some really good questions there. CBSE foreign is tougher than CBSE All India. We have prepared some revision assignments also for the first, second, third, fourth chapters. These are some tough chapters. So they will share that assignment on the group itself. That assignment is divided into levels. So for your boards, level 1 is sufficient. So just try to go through questions of level 1. Please tell me once you have noted this diagram on this side.
Yes, sir. Draw.
Can we keep one extra class on this coming Friday evening, same time? I need some extra classes. Huh? Although I'll inform you on group about the Friday extra class. Okay, I'll stop here. In the next class, we will start with the calculus, a very small topic. We'll try to finish in the next class on interaction. And then we will be left in only with one major topic, and that is ray optics. After ray optics, we have modern physics. Modern physics is straightforward. Always will stop here.